This is section 6.6. We're going to perform similarity transformations. A dilation is a transformation that stretches or shrinks a figure to create a similar figure. A dilation is a type of similarity transformation. So for example, let's say you have a figure like this small blue triangle. We could stretch it so it looks like this red triangle that's bigger. These would be similar if you use what's called a dilation. Now, you could also dilate or shrink this larger figure into this smaller one. If you do that, again, the figures would be similar. In a dilation, a figure is enlarged or reduced. So small to large would be the enlargement. Large to small would be the reduction, with respect to a fixed point called the center of dilation. Everyone that we use or we see, the center of dilation is going to be the origin. And here's how this works. Notice how if we connect these corresponding vertices A and X, notice how it originates from the origin. We can go from the origin through A and through X. Likewise, B and Y, those vertices correspond. If you go through the origin, you'll go through point B and point Y. Same thing with point C and point Z. Go from the origin through C through Z. The scale factor of a dilation is the ratio of the side length of the image to the corresponding side length of the original figure. So for example, if these sides correspond, then you can write this ratio, whatever this is, divided by that, that's your scale factor. You're going to see coordinate notation for a dilation as well. You can describe a dilation with respect to the origin with this notation. Your ordered pair XY is going to be mapped to a new ordered pair, where you're going to multiply both X and Y by the same number. And that number we're going to call K. That K is your scale factor. So K is just a number. Now, when K is bigger than 0 and less than 1, what's going to happen is the dilation that you're using is going to be a reduction. Because if you multiply something by a number less than 1, you're going to shrink it. If you multiply something by a number bigger than 1, you're going to enlarge it. So if your K is between 0 and 1, you're reducing. If K is bigger than 1, you're enlarging. Let's try one. We're going to draw a dilation of a quadrilateral ABCD, with vertices here that are given. Notice how you have an X and a Y for each of them. We have them plotted already. If these weren't graphed, then you could plot them yourself and make the shape. We're going to use a scale factor of 2. So notice how I have all of my ordered pairs written down for points A, B, C, and D. I'm going to take my scale factor of 2. Notice how 2 is bigger than 1, so this is going to be an enlargement. And I'm going to multiply these ordered pairs by that scale factor. So if A lives at 2, 1, point L is going to be what this corresponds with. We're going to say it lives at 4, 2. All I did was multiply this by 2 and multiply this by 2. So you do the same thing for every single ordered pair. We'll make this the ordered pair 8, 2. We'll make this one the ordered pair 8, negative 2. We'll make this the ordered pair 2, negative 2. Then we're going to plot all of these. There's your 4 ordered pairs. I'm going to try my best to connect these. Yeah, not doing so bad so far. This diagonal one's going to be tricky. All right, not too bad. So this blue shape has been enlarged to look like this red shape. and I'll even put the coordinates on here. That was L, that was M, that was N, and this is P. Now, the center of dilation, remember we've talked about this, that starts at the origin. So if I go through the origin, I could connect A with L. B goes with M. Notice how this is working out. That means these two figures are similar. A dilation is a similarity transformation. So that's kind of cool. We'll do this last one here. Verify that a figure is similar to its dilation. So we have a triangle with these ordered pairs. Notice how it's not plotted. So we'll do that. We'll put A at 4, -4. We'll put B at 8, 2. We'll put C at 8, -4. Okay, so I can tell immediately that this is a right triangle because I have a horizontal segment and a vertical segment coming together. You know lots of things about right triangles. I'll even put this on here since I know this already, and it'll come in handy in a little bit. The image of triangle ABC, because where's A? This is A. Whoops. A. B would be this guy. And C would be this guy. The image of triangle ABC after a dilation with scale factor 1/2 is triangle DEF. So if we're using a scale factor of 1/2, that means our figure that we're going to make next, we're actually shrinking this figure to make this figure. So if we multiply by 1/2, you're basically dividing all of these by 2. So 4, -4 would become 2, -2. 8, 2 would become 4, 1. 8, -4 would become 4, -2. And then we'll just plot these the same way that we did points A, B, and C. There's point D. There's point E. And here's point F. Yeah, 4, -2. Right there. And again, notice that we have a horizontal segment coming together with a vertical segment. That definitely makes a right angle. These are guaranteed to be similar. Now, they want you to prove that it's similar. So we already did part A. We sketched both triangles. And this is going to be tough for you to do unless, if you're not printing out your homework and your notes, it's going to be really hard for you to plot this, especially if you don't have graph paper. I would say just do your best. Verify the triangle ABC and triangle DEF are similar. Well, we have a lot of ways to show the triangles are similar. We could use angle-angle or side-side-side or side-angle-side. Notice how we already have congruent angles. And notice how this is horizontal and this is vertical. Same thing here. We can count these lengths. This is 2. This is 3. We're going to do the same thing with this one. This is 4. This is 6. Do you agree that they're similar? 2 to 4, 3 to 6. That's the same ratio. You have right angles in between. So they're similar by side angle side. Okay, so when you enlarge or reduce something, it is a similarity transformation.